In the name of Allah, the most beneficent and the most merciful. May peace, mercy, and blessings of Allah be upon all of you. Let we start with the recitation of the Holy Quran by Hafiz Muhammad Imran Khan.
أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. فلا أقسم بالخنس الجوار الكنس والليل إذا عسعس والصبح إذا تنفس إنه لقول رسول كريم ذي قوة عند ذي العرش مكين مطاع ثم أمين وما صاحبكم بمجنون ولقد رآه بالأفق المبين وما هو على الغيب بضنين وما هو بقول الشيطان الرجيم فأين تذهبون إن هو إلا ذكر للعالمين لمن شاء منكم أن يستقيم وما تشاءون إلا أن يشاء الله رب العالمين صدق الله العظيم.
جزاک اللہ. کاش وہ چہرہ میری آنکھ نے دیکھا ہوتا، مجھ کو تقدیر نے اسی دور میں لکھا ہوتا. باتیں سنتا میں کبھی پوچھتا مانی ان کے، میں آپ کے سامنے اصحاب میں بیٹھا ہوتا. ہر سیاہ رات میں روشن ہے حدیثیں ان کی، آپ نہ آتے تو زمانے میں اندھیرا ہوتا. صلی اللہ علیہ وآلہ وسلم. مسٹر حمزہ اکبر will come for the نعت رسول مقبول.
در نبی پر پڑا رہوں گا، پڑے ہی رہنے سے کام ہوگا. کبھی تو قسمت کھلے گی میری، کبھی تو میرا سلام ہوگا. خلاف معشوق کچھ ہوا ہے، نہ کوئی عاشق سے کام ہوگا. خدا بھی ہوگا ادھر بھی ہے دل، جدھر وہ والی مقام ہوگا. در نبی پر پڑا رہوں گا، پڑے ہی رہنے سے کام ہوگا. کبھی تو قسمت کھولے گی میری، मेरी कभी तो मेरा सलाम होगा.
Thank you, Hamza. And now let we all rise for the national anthem, please. Worthy chief guest of the ceremony, Vice Chancellor Allama Iqbal Open University, Professor Dr. AIOU, Honorable Guest of Honor from abroad, Professor Dr. Khalid Hafiz, distinguished delegates, dear colleagues, professors, lecturers, researchers, ladies and gentlemen, Assalamu alaikum and a very good morning. On the behalf of Allama Iqbal Open University and the Department of Physics, I, Harim Mufti, would like to express my sincere gratitude and a very warm welcome to all of you on the opening ceremony of our 6th International Conference on Nanomaterials, Modeling and Simulation 2021. Ladies and gentlemen, this is the 6th spell of the series of our International Conference on Nanomaterials, the most advanced and highly approached area of research these days. The focal drive of this conference is to exchange ideas, and by participating in this exchange, it is hoped that all parties who may benefit from the conference can apply it in managing activities in their areas. We all hope that this time we will, inshallah, achieve its objectives in providing an effective forum for all of you to advancing knowledge, research, and technology for humanity. It is pleasing to note that the agenda of this conference covers a wide range of interesting topics related to all theoretical and experimental aspects of nanomaterials and their simulation. Dear audience, I would like to call upon now the chief organizer of this event and Chairman, Department of Physics, Professor Dr. Syed Zafar Ilyas, for the introduction and the welcome address. Sir, please.
Bismillahirrahmanirrahim. Honorable Vice Chancellor and Chief Guest, Professor Dr. AIOU Saab, respected Dr. Khalid Hafiz, Dean Sciences, respected teachers, respected participants, dear colleagues, and dear students, Assalamu alaikum. Sir, it's a 6th International Conference on Nanomaterial Modeling and Simulation. The Department of Physics started his journey of the conferences from 2011, and that is the first conference of the Allama Iqbal Open University. And we are the pioneer in the Allama Iqbal Open University to start the conferences series in Allama Iqbal Open University. So today, it's a 106th conference, seminar, or training workshop of the physics department within the spell of 11 years. Sir, in this conference, 110 paper will be published, presented, oral presented, and 18 paper will be poster presentation. That is 128 paper will be presented in this conference. Almost 70 universities from all over the Pakistan, Balochistan, Punjab, KPK, Sindh, GB, and Azad Kashmir. All the universities from these areas are presenting their paper in this conference. 6 papers from abroad will be presented in this conference. Dr. Khalid Hafiz is here. We are very thankful to come out to the Pakistan in this crisis and this COVID-19 problems. Very thankful to him. And we have another event over there, that is the presentation of the MSc final projects, and as well as very thankful to the Women University, Multan. They are participated and very much participated in this conference. They are presenting their paper, and as well as they are presenting their projects in this event too. So these are the 2 events in this conference. One is a paper and the other is a projects presentation. I'm especially very thankful to the keynote speakers from all over the Pakistan, mostly Punjab, KPK, Balochistan, and as well as from AJK. So they come over, and I hope they will enjoy the stay and enjoy the weather. If there is any problem, so we are here. This conference is totally supported by the Vice Chancellor. We are not receiving any fund from anyone. So not from the HEC, not from Pakistan Science Foundation. So the 2 things, the academic and the research, that what the Vice Chancellor never says no's in these 2 areas. So we are very grateful and thankful to the Vice Chancellor for supporting and presenting this conference. Thank you very much and welcome you all over here.
Thank you very much, sir. We are but a fleeting moment of eternity, a moment intensely packed with joy and tears. We can do little but to accept what comes along and find our joy in helping those who need it most. For it is only by lighting the flame in others that we can illuminate our own soul. These are the beautiful lines by a brilliant scientist and a master of his field, an asset of Pakistan, and a great human being, Professor Dr. Ataur Rahman. The Honorable, he is a PhD in organic chemistry from Cambridge University. He has 1,267 international publications in several fields of organic chemistry, including 781 research publications, 50 international patents, 70 chapters in books, and 366 books published largely by major US and European presses. He is the editor-in-chief of several European chemistry journals. He is the editor of the world's leading encyclopedia series of volumes on natural products. 83 students have completed their PhD under his supervision. He is holding 16 national, 19 international awards, and 9 fellowships. He is also the Professor Emeritus, Patron-in-Chief in the International Center of Chemical and Biological Sciences in University of Karachi. And now he's serving as Chairman, Prime Minister Task Force on Science and Technology since 2019. Due to his busy schedule, we were unable to bring him here, so we have a video talk of Professor Dr. Ataur Rahman. Please.
Assalamu alaikum. A very good morning to all of you. I'd like to welcome all the participants to this conference, and I hope you have a very enjoyable and a stimulating event. I will be talking to you about the wondrous world of science and of chemistry and the amazing developments that are taking place and are impacting our lives in many ways. Let me begin by showing you a paper which has appeared just a few days ago on 29th of November 2021, describing the development of a very tiny camera, an ultra-compact camera. ये नमक के दाने के बराबर है. It's like the grain of a salt. If you see that finger, you see a little this transparent square camera sitting there. Well, that is a wonderful example of nano optics for high quality imaging. And this system can produce excellent quality images which are at par with the camera which has a lens which is 500,000 times larger in volume. So this is an example of what is going on. In Pakistan, we have seen a complete change in the landscape of higher education due to the policies that I introduced when I was the Minister for Science and Technology back in the Musharraf era, and later when I was the Chairman of the Higher Education Commission. At that time, we brought in certain reforms, which I will refer to a little later, but this graph is interesting. This is taken from the Web of Science and compares Pakistan's research output with India per capita, per 10 million individuals. If you look at the extreme left, Pakistan is green and India is red in these bars. Pakistan had only 44 publications per 10 million population. India had 172. We were 400% behind India. Then the result, this whole scenario started changing, and in 2018 we caught up with India, 17 and 18, and now we are about 15 or 20% ahead of India in terms of international publications. In numbers, of course, we are not ahead, but in terms of per capita output, we are ahead. This graph has now been taken from Scopus, and again, this shows that we have caught up with India, more or less. So this is no small achievement for a country like Pakistan, since India had started its investments in science far ahead of us from the Nehru days when they set up the IITs and have been investing heavily in science. So I will describe a little about what led to these changes, which were then applauded by Professor Michael Rode, the chairman of the United Nations Commission on Science, Technology and Development, who wrote that in no other country has the higher education sector seen such spectacular positive development as that in Pakistan. This was in 2008, very soon after I resigned from the Higher Education Commission. And more recently, about 5 years ago, Thomson Reuters wrote an article which was headed Another Brick in the Wall, BRIC, comparing Pakistan with Brazil, Russia, India, and China, and wrote that Pakistan has emerged as a country with the highest percentage of highly cited papers as compared to the BRIC countries. So something really exciting was going on, and India became concerned at what was happening. And a presentation was made to the Indian Prime Minister about what I was doing on 22nd July 2006, and this was reported in the Hindustan Times under the heading Marked Threat to Indian Science, and talked about how Pakistan may soon join China in giving India serious competition. Subsequently, India decided to close down its University Grants Commission, as Pakistan had done, and now they have formed an organization called HECI, Higher Education Commission of India. When I was appointed as the Federal Minister for Science and Technology by President Musharraf, and later Chairman of the Higher Education Commission, I convinced President Musharraf to start investing heavily in science and higher education. As a result, there was a 6,000% increase in the development budget of science and technology, and later a 3,500% increase in the budget of higher education. And we focused on quality of education. Of course, access and relevance were relevant as well. And we also decided that universities should be strengthened by improving the quality of the faculty. And so we identified some 11,000 students, sent them abroad to top universities after a vigorous selection process, and attracted them back to Pakistan through excellent salary structures, through a new tenure track system under which a professor's salary was made 4 to 5 times the salary of a federal minister in the government, access to liberal research funding. Every student would apply for a $100,000 research grant 1 year before they were going to return. Access to lit materials, also finding many applications. For instance, scientists have learned how to change the genetic structure of materials, and so some scientists have taken the genes from the deep sea jellyfishes or from the firefly, the Juno की genes होती हैं, and put them into flowers, and lo and behold, you have luminescent flowers which glow in the dark. Similarly, fascinating applications are taking place in various areas of genetics. Molecular scissors have been developed, so you can cut a gene from one plant and insert it into another plant, and this means that you can create new species in the lab, which used to take thousands or tens of thousands of years to develop. Now you can develop new species of plants or animals within a matter of weeks by using such gene editing techniques. I've talked about 3D printing. Here is a living 3D printed kidney, where you take human kidney cells and spray them layer by layer, and you produce a part of a human kidney. So I would like to end now by thanking you for the opportunity to talk to you about this wondrous world of scientific discovery and how our lives are being transformed. Pakistan has about 2/3 of its population below the age of 30. 67% of our population is below the age of 30. In order to move forward, our governments and the planners must realize that we need to unleash the creative potential in our youth. It is only through massive investments in education, in science, in technology, in innovation and entrepreneurship that we can move forward. I would like to thank you again, and I hope that you have a very interesting event and that you have this opportunity to discuss amongst each other and to collaborate together so that we can move forward rapidly on the road to developing a strong knowledge economy. Thank you very much. Assalamu alaikum.
Thank you very much, sir. We are really honored for his valuable remarks. And now, a few lines for the chief guest of the ceremony, Professor Dr. AIOU. संगे बेकीमत तराशा और जौहर कर दिया, शम्मे इल्म आगही से दिल को मुनव्वर कर दिया, फ़िक्र फ़न तहज़ीब व हिकमत दी शऊर व आगही, गुमशुदाने राह को गोया के राहबर कर दिया, चश्मे फैज़ और दस्त वो पारस सिफत जब छू गए, मुझको मट्टी से उठाया और फलक पर कर दिया, दे जज़ा अल्लाह तू उस बाग़बाने इल्म को जिसने गुंचों को खिलाया और गुलतर कर दिया, खाकाए तस्वीर था मैं खाली अज़ रंगे हयात, यूं सजाया आपने मुझको कि कैसर कर दिया. Distinguished guests, it is about a senior IT level IT professional with more than 30 years of experience in administration, teaching, and research at the university level, having sound competencies of strategic planning and direction, organizational planning, IT governance, and project management. He has strong leadership and administrative skills. His research interests are in the areas of knowledge representation, data mining, recommendation systems, semantic information retrieval. And above all, he is our team leader, a torch bearer, and a captain of our ship. His vision and mission is meaningful for all of us. And fortunately, it is the first event of our department which will be presided by His Highness. Sir, please.
Bismillahirrahmanirrahim. बहुत काबिल एहतराम. I hope, all of the delegates are from Pakistan, so if you allow me, I would like to speak in Urdu, अगर आपको कोई डेक्ट्रम नहीं है तो. बहुत काबिल एहतराम Dr. Khalid Saab, Professor Dr. Zafar Ilyas, Dean, Faculty of Sciences, Professor Irshad, my colleagues from the university, और मेरे मुल्क से आए हुए तूलो अर्ज़ से असातिज़ा कराम और बहुत अज़ीज़ तलबा तलबात, अस्सलाम वालेकुम रहमतुल्लाह. मैडम साहबा, सबसे पहले तो जो आपने फरमाया, आई फील हम्बल्ड. मैं एक छोटा सा शख्स हूँ जो अपने आप को इस काबिल नहीं समझता है कि इस तरह की बातें शायद उसके बारे में कही जाएँ, तो मैं उस पर فخر کر سکوں. آپ کی مہربانی ہے, آپ ساروں کی مہربانی ہے. اگر آپ یہ سمجھتے ہیں کہ میں کسی ادارے میں اپنا کو تھوڑا سا کنٹریبیوشن دے سکتا ہوں تو بہرحال یہ آپ کی ذرا نوازی ہے, آپ کی بڑائی ہے. میں ممنون ہوں بہرحال آپ کے ان خیالات کا. آئی فیل ہمبلڈ آنیسٹلی. ڈاکٹر صاحب آپ کو مبارکباد پیش کرتا ہوں. آپ نے جو فگرز شیئر کی, میری تھوڑی سی کوتاہی کہہ لیجئے یا بھلے سے مصروفیت کہہ لیجئے, جو بھی اسکیپ کا ذریعہ ہو سکتی ہو بات, کہ آپ نے کم و بیش آپ نے بتایا کہ 100 سے زیادہ ایونٹس آپ نے آرگنائز کیے ہیں ابھی تک اپنے فزکس ڈپارٹمنٹ میں, اور شیورلی اس سال میں بھی آپ نے ایونٹس ارینج کیے ہوں گے, لیکن میں آپ کے پاس حاضر نہیں ہو سکا. میں بہرحال میں اس سے مستفید نہیں, بلکہ یوں کہ یہ ہو سکا, میں اس کے لیے معذرت خواہ بھی ہوں. لیکن ہم کلیکٹیولی جو ایک یونیورسٹیوں کا کلچر ہے جس میں ہم عمومی طور پہ ہم سارے اس بات سے آگاہ بھی ہیں اور ہم اس کو ری ایٹریٹ کرتے رہتے ہیں کہ یونیورسٹیاں نیا نالج پروڈیوس کرنے کا ذریعہ ہوتی ہیں. یونیورسٹیاں نالج کنزیوم نہیں کرتی, یونیورسٹیاں نالج یوز نہیں کرتی. یونیورسٹیز میں اساتذہ کرام نیا نالج پروڈیوس کرتے ہیں, جو کہ پھر نالج کمیونٹی میں اس باڈی آف ڈومین میں ایک سگنیفیکنٹ کنٹریبیوشن کے طور پہ رجسٹر ہوتا ہے, اور بہرحال کہیں نہ کہیں اس کو استعمال کیا جاتا ہے, لوگ اس سے استفادہ کرتے ہیں. اور مجھے خوشی ہے اس بات کی کہ آپ کا ڈپارٹمنٹ آپ کی سربراہی میں ماشاءاللہ ریسرچ ایکٹیویٹیز کو پروموٹ کرنے میں اپنا بھرپور کردار ادا کر رہا ہے, اور ان جنرل فیکلٹی آف سائنس بھی. بلکہ مجھے یہ کہنا چاہیے کہ چونکہ یہاں پہ ہم ایک اوپن یونیورسٹی ہونے کے ناطے جو نظام تعلیم ہے ہمارا تھوڑا سا مختلف ہے باقی جنرل یونیورسٹیز سے, اور فیکلٹی آف سائنس ہمارا وہ ایک واحد کمپوننٹ ہے جہاں پہ ایک فارمل ایجوکیشن سسٹم میں ہم اپنے طلباء طالبات کو پڑھا رہے ہیں, ان کی گرومنگ کر رہے ہیں. فیکلٹی آف سائنس پھر اس حوالے سے اس کمپیریزن میں بات کر رہا ہوں کہ بڑی پروڈکٹیو ہے ان ٹرمز آف پروڈیوسنگ نیو ریسرچ اینڈ رجسٹرنگ دیئر پریزنس ان دیئر پیئرز ان اے ریسپیکٹیبل فیشن. جہاں تک اس کانفرنس کے موضوع کی بات ہے, ایک اور بڑی امپورٹنٹ بات وچ I think I owe to mention is the leadership of the department, کہ کانفرنسز کو سوچنا اپنی جگہ پہ ایک مشکل کام ہے, لیکن پھر کانفرنسز کو آرگنائز کرنا اس ٹیم کے ساتھ, اس کی لیڈرشپ لینا, لیڈرشپ کا چیلنج اسیوم کرنا, اور پھر اس سے زیادہ امپورٹنٹ یہ ہے کہ اس کو آپ ہر سال ایک ریگولر ایونٹ کے طور پہ رجسٹر کریں. اٹس این اپ ہل اینڈ چیلنجنگ ٹاسک جس میں آپ اور آپ کی ٹیم بہرحال مبارکباد کی مستحق ہے. جہاں تک اس موضوع کا تعلق ہے, میں بڑے عرصے سے کوشش میں ہوں کہ میں کوانٹم کمپیوٹنگ پہ تھوڑا سا پڑھ سکوں, لیکن اس بات کو کرنے سے پہلے آئی واز جسٹ ٹرائنگ ٹو ریکلیکٹ جو میرا فیلڈ بہرحال چونکہ کمپیوٹر سائنس ہے, تو میں ریلیٹ کرنے کی کوشش کر رہا تھا جو کچھ آج آپ بات کرنے جا رہے ہیں اس کو اپنے ڈومین میں یا اس کی جو اپلیکیشنز ہو سکتی ہیں اس کو میں اس کے بارے میں سوچنے کی کوشش کر رہا تھا کوئکلی جب میں یہاں پہ بیٹھا تھا. اور بہت عرصے سے جب ہم کوانٹم کمپیوٹنگ کی بات کرتے ہیں تو یہ ایک ریولیوشن ہے بہرحال میری کمپیوٹنگ کے ڈومین میں, اور آپ سارے اس کے کسی نہ کسی حوالے سے یوزرز ہیں. تو اس بات کو سوچتے ہوئے مجھے یاد آیا کہ اگر آپ تھوڑا سا پیچھے چلے جائیں, میں تھوڑا سا اس لیے کہہ رہا ہوں کہ میں یہ نہیں کہنا چاہتا کہ میں بہت بوڑھا آدمی ہوں. سو وین یو ہیڈ دا ٹی وی سیٹس جو کہ میرا خیال ہے کہ اس ٹیبل کے سائز پہ بڑی مشکل سے رکھے جاتے تھے, وہ جو اینالاگ ٹی وی تھے ہمارے جس میں پکچر ٹیوبز لگتی تھیں اور ایک اسپیسیفک سرکٹری تھی. میں نے آئی کوڈ ریکال اینڈ ریکلیکٹ, میں میتھمیٹکس میں میری پہلی ماسٹرز تھی تو میں ملتان سے پڑھا, تو ہمارے لیے ایک تو اسلام آباد آنا, جیسے آپ میں سے بہت سارے لوگ آئے ہوں گے, تو ایک بہرحال اسٹوڈنٹ لائف میں اپنی جگہ پہ وہ ایک اٹریکشن بھی ہے, اور دوسرا یہ تھا کہ کمپیوٹر دیکھا جائے. سو آئی مین لک ایٹ دا پیس آف ڈیولپمنٹ, دا پیس آف ٹیکنالوجیکل ریولیوشن جو آئی ہے پچھلے خصوصاً تقریباً 20 سال میں. سو مجھے یاد ہے کہ ہم قائد اعظم یونیورسٹی گئے اور ایک شیشے کے باہر کھڑا کر کے, یعنی دیر واز اے گلاس پارٹیشن, اینڈ وی ور ٹولڈ اوکے وہ کمپیوٹر ہے, اینڈ یو کین امیجن ہم کمپیوٹرز کے جب پڑھاتے بھی ہیں تو ہم یہ کہتے ہیں کہ جو سائز اور والیوم آف دا مشینز تھا جو کہ شاید ایک گڈ ہنڈریڈز آف اسکوائر فیٹ کے کمرے میں پہلے کبھی ایک کمپیوٹر ہاؤس ہم کر سکتے تھے. اور میں نے اپنے اس استعمال کرنے والے دور میں بھی کمپیوٹرز کے سائز کو دیکھا ہے, ان کی پرفارمنس اور ان کی ایفیشنسی کو اگر آپ ٹریس بیک کریں صرف یہ 90 کی دہائی سے آنورڈ اگر آپ چلنا شروع کر دیں, ہم اسمبلی لینگویج میں x86 مشینز پڑھاتے ہوتے تھے اور آج وہ آبسلیٹ ہیں, وہ کانسیپٹ آبسلیٹ ہیں. نالج کی حد تک ضرور بچوں کو بتانے کی ضرورت ہے, لیکن آج آپ دیکھیں تو جو موبائلز ہمارے پاس ہیں ان کی پرفارمنس شاید اس آج سے تقریباً کو 20 سال پہلے کی جو مشینز تھیں اس سے بہتر کمپیوٹنگ پاور ان میں ہے, اس سے بہتر میموری فیسلٹیز اس میں ہیں. ڈاکٹر پروفیسر عطا صاحب ابھی ایک نینو اسکیل کے کیمرے کی بات کر رہے تھے. سو لک ایٹ ایکچولی the revolution this technology has brought in for the good of this humanity as well. And most of these concepts are coming from these interdisciplinary domains of physics, I mean something from maybe chemistry, I guess. I mean taking analogies from that domain. And computer science is basically beneficiary of this interdisciplinary research. The quantum computing directly is basically manifestation of the confluence of the domains of nanotechnology, material science, and the quantum mechanics. اور جس کی وجہ سے آج جو سپر کمپیوٹنگ کا جو کمپیوٹنگ پار جو آج مشینز میں میسر ہے اور اویلیبل ہو سکتی ہے, جو اسکیل ریڈکشن ہے سائز آف دا مٹیریلز کی اور ان کی ایفیشنسی کی, دس از فینومینل. سو اس بات کو صرف نشاندہی میں اس بات سے کر رہا تھا کہ ہمیں نہ صرف بیسک ریسرچ کرنے پہ ضرورت ہے, اس میں کوئی دوسری رائے نہیں ہے. چونکہ جو بیسک ریسرچ ہے وہ سبجیکٹس کی ڈیولپمنٹ میں, باڈی آف نالج میں اضافے کا ضرور بہرحال باعث بنتی ہے, لیکن دیر از اے اسٹرانگ نیڈ اپنے ملک کی اکانومی کو سامنے رکھتے ہوئے, اپنے ملک کی نیڈس کو سامنے رکھتے ہوئے اس بات کی بڑی اشد ضرورت ہے کہ ہم انٹر ڈسپلنری ریسرچ کو بھی فروغ دیں. دس سم تھنگ وچ آئی ریئلی وانٹیڈ ٹو برنگ فارورڈ, جو گفتگو میں آپ سے کرنا چاہ رہا تھا. آج اگر ہم یہ سمجھتے ہیں کہ ہم اپنے سائلوز میں رہ کے ہم بڑا سگنیفیکنٹ کام کر سکیں گے, فزکس والے یا کوانٹم فزکس والے صرف کوانٹم پہ کام کر رہے ہیں, آپٹرانکس والے آپٹرانکس پہ کام کر رہے ہیں, کوئی الیکٹرانکس والے صرف اپنی ان باؤنڈریز میں رہ کے اور سائلوز میں رہ کے کام کریں گے, ہم کمپیوٹر سائنس والے سمجھیں ہم بڑے بہرحال پتہ نہیں کمال کے لوگ ہیں آج 21ویں صدی جو کہ ٹیکنالوجی کی صدی ہے, جو ہمارے بغیر شاید نہیں چلتی, تو اس میں یہ ہماری خام خیالی ہوگی. سو ڈاکٹر صاحب اس بیس لائنس کو اچیو کرنے کے بعد ماشاء اللہ آپ کی فیکلٹی میں کیمسٹری از پرفارمنگ ویری ویل. سملرلی آپ کے پاس بایولوجیکل سائنسز کا پورا ایک ڈپارٹمنٹ ہے, کمپیوٹر سائنس آپ کے ساتھ ہے. کمپیوٹر سائنس کو ہم اسٹرینگتھن بھی کر رہے ہیں, کچھ نئی فیکلٹی نے جوائن کیا ہے ہمارے ساتھ, اور انشاءاللہ اگلے کچھ عرصے میں کچھ نئے لوگ اور بھی جوائن کریں گے ہمارے ساتھ. سو آپ اپنے آپ کو ڈاکٹر صاحب کی صورت میں پروفیسر آف اسٹیٹسٹکس ہیں, جو کہ آپ کو ریسرچ پریکٹسز اور میتھڈالوجی کی ایک بڑی اسٹرانگ فاؤنڈیشن بھی دے سکتے ہیں ایکسپیریمنٹیشن کی حد تک. سو میری گزارش ہوگی کہ اگلے کچھ عرصے کے لیے آپ اپنے ٹارگیٹس طے کیجئے, بیسک ریسرچ کے ساتھ ساتھ کچھ ایڈیکویٹ پرسنٹیج, سگنیفیکنٹ پرسنٹیج آف دا ریسرچ پروجیکٹس شوڈ بی ریلی focused on solving the indigenous problems of this country, using the research which is produced by your groups, for example, or I mean elsewhere in the country or internationally. Let's use that baseline, that research as a baseline concept, and then evolve actually the concepts over it, solve the problems of this country. ہمارے پاس بہت زیادہ پیسے نہیں ہیں کہ ہم ہر چیز لا کے اپنے ملک میں استعمال کر سکیں. ہمیں انڈیجنس سولوشنز بنانے کی ضرورت ہے تاکہ ہم اس ملک کی ترقی میں اپنا کردار ادا کریں. اور عام طور پہ اگرچہ ہماری کوئی انویسٹمنٹ بہت بڑی نہیں ہے جو ہم ہائر ایجوکیشن سیکٹر میں کرتے ہیں اپنے ایون نیبرنگ کنٹریز کے ساتھ اگر ہم کمپیریزن کریں, لیکن بہرحال جتنے بھی ریسورسز اویلیبل ہیں یہ ملک اربوں روپے ہر سال ہائر ایجوکیشن سیکٹر پہ صرف کرتا ہے. تو ہمیں بہرحال پے بیک کرنا اب شروع کرنا چاہیے. ماشاءاللہ ہمارے پاس اب کوالیفائڈ فیکلٹی ہے. آپ کی ڈپارٹمنٹ میں میرا خیال ہے ہم نے میکسیمم انویسٹمنٹ کی ہے لیب اسٹرکچر اپ گریڈیشن پہ بھی, اور ان جنرل فیکلٹی آف سائنس میں بھی. وی ہیو اسپینڈ hundreds of millions, I guess, ان 2 سے 2.5 سالوں میں ان لیب انفراسٹرکچر اسٹرینتھننگ پہ اس کے فروٹس جو ہیں, جو اس کے بینیفٹس ہیں, وہ ان بچوں کو ملنے چاہیے. اساتذہ کرام اس طرح سے ریسرچ کریں, اور بہرحال ریسرچ ایسی جو میننگ فل ہے, جو ریلیونٹ ہے, ریلیونٹ ٹو دا نیڈز آف دا سوسائٹی ہے, ریلیونٹ ٹو دا نیڈز آف دا نالج کمیونٹی ہے, اس پہ فوکس کرتے ہوئے ہم اپنی ریسرچ ایکٹیویٹیز کو آگے لے کے چلیں. آخر میں پروفیسر صاحب آپ کا پھر شکر گزار ہوں. خالد صاحب آپ تشریف لائے سر. اینڈ آئی سیڈ ٹو ڈاکٹر صاحب کہ ویلکم ہوم, آپ گھر میں ہیں سر, آپ اپنے ملک میں واپس تشریف لائے ہیں, اور مجھے بہت یقین ہے آپ سب بھی اور جو میرے باقی کالیگس جو کہ اس کانفرنس میں پریزنٹ کریں گے, آپ کا ایک خوشگوار اسٹے ہوگا اسلام آباد میں. میں اسلام آباد کو کہیں بھی کانفرنس میں باہر جاتا ہوں تو میں ان سے کہتا ہوں کہ وزٹ مائی city, my country, and enjoy the hospitality of people of Pakistan. لیکن اس سے امپورٹنٹ بات یہ ہے کہ this is one of the most beautiful metropolitan cities of the world, one of the most beautiful capital cities of the world. So visit اسلام آباد. آپ جو ہمارے پاس تشریف لائیں, اور سر آپ بھی ہمارے لائق کوئی بھی سروس ہو, ڈاکٹر صاحب اور ان کی ٹیم آپ کو لک آفٹر کریں گے. آخر میں ڈاکٹر صاحب میں آپ کو اور آپ کی ٹیم کو مبارکباد پیش کرتا ہوں کہ آپ ایک ہیلدی نالج شیئرنگ, نالج ڈسیمینیشن کے فورمز کو پروموٹ کرنے میں اپنا کردار ادا کر رہے ہیں. اور میں شکریہ ادا کرتا ہوں سارے ڈیلیگیٹس کا جو تشریف لائے اور اپنی ریسرچ جو ہے وہ شیئر کریں گے فار دا گڈ آف کمیونٹی. اینڈ آئی ہوپ ونس یو گو بیک آپ بہت سارے نئے آئیڈیاز جو ہیں اس گفتگو کے بعد لے کے آپ واپس جائیں گے اور مزید بہتر کام کر سکیں گے. اللہ تعالیٰ آپ کا حامی و ناصر ہوں. پاکستان زندہ باد.
Thank you very much, sir. Your presence is an honor for us today. And before going to the shield distribution ceremony, I would like to make an announcement that we have the students of our MSc Physics program. They have arranged an exhibition on GSM-based projects. And then the specialty this time is that we have a team from Multan and Lahore as well, especially presided by Dr. Malika Rani. And she is bringing her almost, I think, 50 girls. The basic thing is they are females, all of them. They have bring in the projects with them, and poster sessions will be there also, I think, guess. So after this, I would like you to inaugurate that exhibition as well. Thank you so much for your presence, and hope you enjoy your stay over here. Thank you. We have a bouquet of flowers and a shield for our chief guest, Professor Dr. Zal Qayyum, and it will be presented by Dr. Khalid Hafiz and Dr. Irshad, Dean, Faculty of Sciences. But first time, sir, آپ ہمارے گھر میں آئے ہیں. And now we have a shield to present to Miss Uzma Naveed from Allied Bank. Manager, Allied Bank, if she's here. Or some of his nominee. Now we have a shield for Professor Dr. Aslam Beg, an asset of our physics field. And then Professor Dr. Muhammad Zafar Iqbal. Thank you, Ji. Thank you so much, sir.
بہت شکریہ جی. آپ have a pleasant day and it's very informed session during this day. میں 11 بجے سے 10:30 بجے سے میں کمپلیٹ ہوں, لیکن میں آپ کے مجھے کے لیے حاضر ہو گیا. میں اجازت چاہوں گا پھر کہیں پہ انشاءاللہ
Dr. Khalid Hafiz, and he'll proceed further. Thank you, sir.
Bismillahirrahmanirrahim. Assalamu alaikum and good morning. I think I'll start with my thanks to the hosts, Professor Zafar Ilyas and the team, and my co-chair, Professor Dr. Syed Javed Khurshid Sahab, if you allow me. So I think the first talk is for myself here to start off with the warm-up session. That's what we call it. And it's not going to be a very technical session. I'm not going to talk about nanotechnology, nanomaterial, but I'll touch upon something which Dr. Atul Rahman mentioned this morning, and where he was doing the comparison between Pakistan and India in terms of research publications. So what it shows is a lot of research is going on in different universities, so which is good sign, and publications are going on and quality of that is improving, which is very good sign. But I think the second thing he touched upon was about excite young minds, and excite young minds about the wonders of science. And I think this is equally important. It's not only important that you are a scientist, so that is a good thing to have, but the idea is that, okay, once you have the science and you have a good ideas what to do with it. So my talk is about that especially, a lot of my honorable teachers, professors sitting in here, and a lot of students sitting in here, and lots of students in making to become professors sitting in here. The idea is what to do, how you can train yourself that once you have some good ideas, you can go out and you can use it for the benefit of something. Otherwise, you end up with writing a paper and nobody read that paper, and after that, what? But the idea is that science has to be for the benefit of people, for society, for industry, for business community. So that's what it is all about. So what I'm going to talk about a little bit is about the new movements which are taking place in the UK experience at the universities, that open innovation. So you might have heard about innovation in the past, innovation in new things, new ideas, which is all good to have, and all of you working on some kind of inventing something. But how you can use innovation in terms of open innovation. And this is what I'm going to give you some examples of that, how universities are using open innovation as an engine of growth, as an engine of productivity, as an engine with working with the collaborators, and training students for employability, training students to become a better scientist. So that's the agenda, which I mentioned already, so I won't go back on this. So what is the difference between open and closed innovation? And I'm sure that all of you know about closed innovation. What is innovation? Coming with something new idea, new product, new service, new thoughts, new organization, new process. So a lot of things where you can bring something new. So the open innovation is a paradigm that assumes that firms can and should use external sources. So a lot of time with the closed innovation, you're using internal resources. You have labs, you have scientists working in there, you work with each other, and maybe your professors, you're working together to create ideas, collaborate, and come up with the advancement in your technology, your formula, your specimen, your code if you're making it, if you're let's say computer scientist. I was looking at the exhibitions upstairs. But this is something which is the earliest person, Dr. Henry Chesbrough, who's the executive director, Center for Open Innovation at Haas School of Business. And this is what he says, that open innovation is that you utilize internal sources as well as external sources for which you don't have control on. And that's what I'm going to concentrate upon. So the open innovation aims to exploit external ideas presented by your consumers and partners to achieve market success. So, for example, if you're coming up with something in a new kind of a device, a new mobile phone, new computer, or even a simplest idea, then you use your customers who will be the end beneficiary, who will be using it. Because if you invent something which is only good for yourself and you understand it, then that's not going to get to the marketplace. So unless your consumers, unless your end users using it, they can bring you ideas so you can work on that. And the marketplace is very important. Your competitors and your other industry partners who are working in similar ideas. So is there a way you can access to that? And the benefit of that is so great. It will avoid you risks. Because if you're doing innovation, for example, you're working on your idea, your PhD student, it will take you 4 years to work on. And after 4 years, you find out this idea is going to work because you had some consumers who are going to use it. As in, when you develop that idea, there is a market for it. There is industry to take it on. So all the costs which involve in terms of risk, that you create something and nobody is using it, you wasted your 4 years and you wasted all resources, you save all that risks. You save your time, you save your energy, and you save your dedication because you can use your 4 years doing something else which is useful for somebody else. So that's what it is in terms of using your ideas to save your risk and time and dedication. And open innovation is not something new. It's been going on for a long time. I know the young minds sitting at the back, maybe you have used computer games. Even now you must be using computer games. So once the earliest computer games came about, people were using mod communities, modification communities. So they will bring up I'm from the time, we used to use the space invaders. So there was a kind of something which is bumping from upstairs, like a mesh thing, and you have only a keyboard and you're turning right and left and you're firing at it. You're also a spaceship. So that was the easiest one which you use. So even at that time, the computer game people, they come up with the platforms that you can generate your own games. You can create your own avatar, you can give them power, you can give them a specification. And the users were given the charge of doing that modification, and that you can create those inventions. And those computer games, which a lot of people were using those modifications, they started turning that into another game because they know people like that game. Same way, toy manufacturing, they use this user involvement for a long time. They have labs in which you have, if they're creating a toy for an age of, let's say, 7 to 11 years old, they put them toy and they put people in, those kids in, and they see that, okay, how they play with them, how long they spend, how their span time is, and how much they attract with the different colors, for example. And these are no risk associated in terms of harming them. They're not going to swallow it. So toy manufacturing has been using it their consumers as a part of their innovation system. Xerox company, they have a very famous case study. They won up with the Xerox, the photocopying machine. They have created a whole community of practice. They're engineers, service engineers. They're working all around the globe. They created this virtual platform where people were sharing their ideas that if you have a problem, that is a solution which works. And psychology and behavior labs, which is the consumer marketing, there's a lot of field involved in there, which is bringing those external sources into innovation process. So this was saying that, to summarize, open innovation is not a new idea, but it is a way to implement the companies in a way that picking up again a pace. And I'll give you a number of examples to that. And I think I have 4 or 5 examples to show how open innovation is used by companies, by the industry, and used by the universities and university students to tap into it. So the quote I'm putting up here is from the General Electric. It is one of the largest company who spend 17 billion in their R&D expenditure, research and development expenditures, and they generate value of every £1, $1 they spend, they get 17 times the return for that in terms of how much value is generated through that. And one of the GE portal is about First Built, and it is a co-creation collaborative platform. So co-creation is you have a number of partners involved in creating something together. And it connecting designers, engineers, thinkers, idea generators, maybe storyline writers. And the idea is that if you get involved with that idea generation, you're not the employee, you're not part of that company, but you're part of generating that ideas on that open platform. And the winning ideas, once the idea is won, by different panel members, it is open for purchase. So GE say, okay, this is a good idea, we're going to purchase it. We'll have the IP of this and we'll pay you some money. And this idea, after that, the idea is taken into their micro factory. So ideas implemented in terms of developing that device or the product which they think is something useful for the market. So what GE, the General Electric, is getting benefit from that. So from these challenges, they are tapping into the talent, future talent all across the world. So they know where the talent exists. They're part of GE ethos, the principles, the values, and they work with them. And what they offer to students, for example, is the students get some scholarships to complete their studies. They might get a one-time cash prize. They might get an opportunity to work on the GE product in-house, let's say a 3-month project, 6-month project, the internship, paid internships. So those opportunities are open for those students, the young minds, to go and get some experience working with that company. And if you know that if you have 6 months on your CV that you work with GE, that will open up doors for your future employment. So that is a great way of getting the employment opportunities. Do remember that in the universities, and I've been there, and I'm sure that my elders here have been here for a long time, we can give you ideas, we can give you knowledge, but we can't give the attitude how to work in the industry. That you have to find out while you work in the industry. And this is what benefit you get through that process of engaging with the company. The second example I have is with NASA. And you think about NASA is such a cutting-edge technology company, why they should be going for the young mind, for young students maybe, to help them in terms of developing something. And one of the examples I'm giving you is that they built, through open innovation, a mathematical algorithm and software code to determine the optimal content of medical kits for NASA's future manned mission. So even in future, they want to send their people, whatever, Mars is their next mission, and they're creating those medical kits which are needed. So what they call it is called, they give it a code name as a top coder, and the key people were there, were the Harvard Business School and London Business School. And what these top coders did, they worked on that idea, they find out solutions, they provided about 3,000 codes for that algorithm. And once they went through the algorithm and they found something which is fit for their purpose, they gave them a cash prize of $24,000, which is a handy money for a student life. And and the interesting thing was that the solution for those codes not necessarily came from the American base. You see that the examples are from UK, Japan, even Indonesia. You think about developing countries. So there are minds who are working on those codes, and from Brazil. So that saved NASA a lot of time and money, because if NASA involved, let's say, 2,833 people in generating that code, even for a month or two, think about how much money will be involved. And here they're not spending money, but they are asking the coders, a lot of them are students, to generate a code. So they saved money, and they didn't have to manage that talent. The independent talent is managing themselves. They're writing code with their own efforts, and they're submitting it. So that saves them time and money. The third example I'm putting for Coca-Cola, I'm sure that many people in here, they love Coke. I'm not by any means promoting Coke here. I don't drink myself any carbonated drink. I know that a glass of Coke has 6 tablespoons of sugar, which is dangerous to life. But I'm just giving an example here. So Coca-Cola started an accelerated program, and they started in 8 cities in the world, their accelerated programs. And one of the reasons for that, they know that people are now health conscious. They want to avoid using Coke. Some people don't like the taste. So what they did in these 8 major metropolitan cities in the world, Sydney, Buenos Aires, Rio de Janeiro, Berlin, Singapore, Istanbul, San Francisco, and Bangalore, so they got what they want to create a different thinking for Coke. They call the Happiness Coca-Cola brand. And this is what they want to bring it through the open innovation model of a freestyle dispensing machine. So what this freestyle dispensing machine does is it gives you a number of options in terms of how much sweetener you want, how much teaser you want, how much lemon pinch you want in there. So it creates a recipe for yourself. So you like some recipe, and it will restore that recipe. And what you do is that next time you say, okay, I want to have same recipe. If you go to their dispensing machine in another city, You can put your card in, that will memorize it, and it will generate you the same code for yourself. My next example is Lego. I'm sure that people with kids, they know what Lego is, a Lego set, and you've been using it, building towers with Lego. And Lego was going downhill. It's one of the very famous, popular companies, but in the 1990s, it's found a downturn in their business. They found out people are not using it, or they're not so much anxious about, because there were so many new things, electronic gadgets were coming in. So Lego went back to people who were using it. So what they say is that people don't have to work for us, to work with us. And that is a very important motto. So open innovation in this COVID world, we know that our universities are struggling. In the past, we could send our students to a local industry a lot. They will spend 3 months, 6 months, 1 year internship, apprenticeship programs, and so on. But now they're closing their doors for the risk aversion. Nobody should get COVID and so on. So the idea is that they say you can work, and you can come and share our website, our platforms, and you can share your ideas. So these Logo community members share and design and Lego picture websites, that ideas are generated for the new product release. So what they do is that people work as a community, as a group, they generate ideas, and then what you have is that they ask people to vote for it, which idea they like, what kind of a new Lego set, what is the new Lego theme they like, for example. So once they understand that there is a lot many people liking that idea, they say, okay, we're going to buy this right of that product. And they will give some small, so it's a revenue share model. Like if you see that, NASA will give for $24,000 for a new code. But what they're saying is, okay, you're part of our process. We'll bring this into market. Once their sales is, you'll get a percentage of that revenue as your benefit, working with the Lego. So one of the new game they brought in through that idea is called Mini Big Bang Theory Lego, and there's a picture given on the right-hand side of the screen, and you can see that the whole family is sitting in there, and which is made up with the Lego, and they're generating those community-based product. And what they have is that the amount of supporters, like people say we like this idea, 10,000 people say we like this idea, they say, okay, we'll create a product, bring into marketplace. So even only with this example of this Mini Bang Bang Theory, it took them about 2 years to develop it online, and then it was another 10 months to bring that project into products level to bring into marketplace. And I think the last example is, I'm conscious of the time, is about Samsung. So Samsung started with the accelerator program. So it's taking a model in different ways. It's still open innovation, but there is a lot more structure to it. So they say, okay, we're starting a number of accelerator programs. So they bring in a collaboration between designers, innovators, and thinkers to focus on different solutions. So what the accelerator program does it, they give a space in different cities. And there is a lab in there, they give some resources, they put some capital in, and they ask people to work together. So it's unlike a Lego design, which is more about conceptual idea, this is more product-based idea. So you need to have a lab where you can test different things together. And what they say, that open innovation for them has four foundations. The first one is partnership team. So commercial partnership with a third party. So third party means it's not owned by that Samsung company, which is one of their consumers or other partners or stakeholders. Second is a venture group, that is R&D investment in a startup. So there are people, the venture capitalists, they look at the ideas and they say, okay, this is a nice idea and I want to put money into this idea. And then they own maybe 50%, 60% of the total revenues of that company. So those venture groups are part of that. The third one is a mixed team. So team is very important. So which is they acquire small teams, fit into Samsung, and they build their products. So these are the inventors actually who are who are part of developing those ideas together. And then the fourth involves the accelerator program itself. So these are some examples. You see that how universities, students can join in different industries. And perhaps while you're working in an open innovation, the question comes to your mind is, or as an industry or as a university, is that, okay, how can I create an effective team to enable to collaborate and co-create? And that is something important. It's while you're working with a product, everything in your hand, you have ownership of that. You can utilize different products. You have your own time scale, how you want to work with it. But if you're working with different people, then their minds and how effectively you can make use of it. So in the COVID situation, while people are not co-located, they're working across different part of the geography, how you can bring them effectively together in terms of managing that team. So that is one of the challenge in post-COVID or new normal world, which, as we call it. And the second thing is, while you're working in the idea generation, a lot of these things are, you think about idea which is tacit. It's not tangible, it's intangible. So how you can bring those ideas while working people abroad, far away. If you're working together, you can explain to them with the body language, sketch, diagram, whatever. But once you're working remotely, then how those ideas which are in your mind, you can make it explicit and you can communicate with the people. So that is a challenge. And the idea which I'm proposing is how you can convert a tacit knowledge into an explicit knowledge. Knowledge sharing, as your Vice Chancellor was talking about as well this morning, it is very important while you work in a team, you work with innovation, you work with the industry, that you have ideas, conceptual ideas, but how that idea is moved, tacit to tacit, two people are working and thinking about ideas. But once you want to put something into paper, into design, into graphical form, or into a writing form, even a Word document, that becomes explicit. So how you convert that into explicit form, and from there you move into a stage which we call it as a combination stage, where you apply it in a real world. So that idea comes into working with the product, services, what is available, what technology is there, to enrich that idea, to make it more workable, make it more feasible, maybe a testing side, we call it as a beta test. And then that idea, once it is workable, then you internalize it within the company, so everybody knows about that idea. Or let's say you have done the design, then people at the factory level should understand what that idea is, and they can create that product. So what this circle, what we call it as this cycle of tacit to explicit knowledge sharing, and a lot of work of this is done in Japan by Noneka approach. And this knowledge sharing model, which is tacit to explicit knowledge, is something utilized and used in different part of the industry. And this is what I'm proposing, that universities can benefit utilizing this model while we're working with the industry outside. I don't want to go into more detail of this, how this model works. Anybody is interested in, you can come to me and I can explain a little bit more. But another example I will see is that if you're working in an industry, is that you have collaborative interests. So you have theoretical interest, and what we call it as innovation ecosystem. So in the ecosystem, as I mentioned, you have a whole range of stakeholders there. You have people who are the inventors, you have people who are putting money in, that venture capitalists, you have people like industry partner, and then you have end users. So that whole ecosystem perspective has to come in. So you're not doing innovation only in your garage, in your lab. You know that who will be the end users, who will be using it. And that saves a lot of effort. And the benefit you get is that, as we mentioned, that you can create a value. It's called value co-creation. What innovation bringing in is the value for yourself, value for the society, value for the industry. So how you can co-create this value, and how you can create this network in which people are working together, that how you can orchestrate or administer that network to make it more efficient. So that what industries are working on in terms of network dynamics, and working with the community building. And one of the key things which I research in is in the virtual network, virtual community practice, like only on a platform, social media platforms, and bringing different people together on that social media platform, give them an idea and convert them into a product or service. So that's something which I've been doing a lot. And there's an example of that which I'm suggesting in here, that you can work, if you work from bottom up. So there's a project level that only few people, 1 or 2 people involved. Then you have a membership network level, you have a lot more people involved from the industry and the partners who are working together on the project. And then the idea is that you bring a whole industry, let's say IT industry. So how many partners on the IT industry? And then you have the network policymakers, IT regulations, laws, communication, satellite networks people. So you're bringing them together in building a form that you start from, let's say, from the grassroots level to the meso level and then to the macro level, where everybody from the industry get involved with it. So I think I'll draw this to a close. And what I'm saying is that the open innovation is valid and is working very effectively nowadays after post-COVID world in micro, small, and medium-sized companies. They are utilizing universities. The students are getting involved through universities or through their own effort. You don't have to go through that. There is a application process. You can just you see there's some open innovation going on there. You send them an email and you show them your credentials, and you can be maybe selected to be part of that team who is working together on co-creation. Now, benefits are market success, improve competitiveness, and solve challenging problems. So that is a benefit for the industry. And as I mentioned earlier on, it reduces the risks, innovation risks, the time risks, and the dedication of people involved for the ideas, because you are working straight with the consumers. You have innovation and you have a user sitting in there, so your innovation is not gone wasted. Otherwise, that maybe out of 1,000 innovations, only one innovation is hitting at the marketplace. So think about the success rate of innovation to a commercial product. And by bringing consumers together, the whole ecosystem together, you are maximizing your chances of being successful. And as I mentioned earlier on, universities are very good sources of engaging for open innovation, and through staff, through student expertise, you can be engaged in that process. We at my university, De Montfort University, we're using a number of MBA students, MSc students, and their master's project. I've seen some of the projects here, but those projects we're working in, they take problem from the industry and they solve those problems actually. So that's what it is going on. So rather than we generating idea we're generating idea within the university, the problems are coming to us from the industry and we are resolving those problems. And then the other ways of engaging with the industry, giving the employment skills to our students, and the attitude actually. A lot of students, we give them knowledge, but not the attitude. Attitude to work in the industry is very different. It's maybe very different in Pakistan. I think it's maybe different in third world countries. You put your CV in and you think, okay, your 99% or 95% of your credentials are in the CV. UK is very different. You put your CV in, usually they shortlist 4 people, and your CV is counted only 25%. What is your qualification is, what experience you have. 75% is resting on your attitude, how you can interact with people, how you can solve a problem, how you can give answers. Because expectation is everybody who's spent 10 years, 5 years, 15 years in working somewhere, you all have the credentials. You can apply for the same job. For example, there's respected people sitting in here, out of 20 people, they apply for the vice chancellor job. Everybody has credentials, but it is about how you solve that problem in that level. So the attitudinal part, you learn only while you work in the industry. And this is where it has become so much useful. And, if you can't work in the industry itself, then the social media platforms, their brand communities, you can access through those information through social media to get that valid experience. So I'll stop in here, and if anybody wants to ask any question, then I'll try to answer it if it's possible.
Can we take
Sure. Okay, that's fine. Thank you very much.
By the way, is your university a private sector university or a public sector?
UK system is very interesting. It is a you can call it as a public sector, but public sector is very mixed. It's not all funding comes from the public, from the government sector. It is they pay students per students, how many students come in, and they pay a portion of that. So UK system is a lot of universities will be public sector universities. Private sector is
100% would be public because
I would say now 90% are public sector universities. I think US has a maybe different model, maybe 50-50, or more private universities where people pay from their fee. International students, they pay their own fee. Local students, they pay a fee from compensated fee, or they get grants. Yeah, privatization with the market Thatcher. Yeah, you're right. Yeah. Yes, if you allow me, sir. And then you can take over while I'm standing here. Okay, so thank you. So I think it's as I'm sitting in here as a co-chair. So my task is to announce the next speaker as well. I don't know how I can get out of it. Okay. So my next speaker, and it's my honor to invite Professor Emeritus Qaid-e-Azam University, Islamabad, Muhammad Zafar Iqbal. And there's a lot in there which I can say about you, sir, but I'll say a few things. So you've been with the Qaid-e-Azam University, Islamabad for maybe about more than 3 years. You worked as a professor and advisor at the ComSat Institute of Information Technology, Islamabad for more than 12 years. And before that, you spent about 40 years in Qaid-e-Azam University. So if I'm not wrong, you've done your PhD from Manchester, UK, in semiconductor. Early days, you might have seen that huge semiconductor computer in Manchester University, which our Vice Chancellor this morning was talking about. So your alma mater is from physics, 1970 to 74. With a postdoc you completed, and master you did in theoretical physics, in particle physics, a specialization in Islamabad. So, and you have a lot of endorsements with the honors, with the Khaliqur Rahman, Muhammad Mutual Connection, Saadat Anwar Siddiqui, and other highly skilled people who have
that's a news to me, by the way.
Well, I think they're doing a very good search for you behind the scene. So I think they found out a lot, and I think without further ado, I will invite you, sir, to give your invited talk.
Thank you. All right. यहाँ से होगा. अच्छा, ठीक है. Okay, thank you. All right. So I like to share this afternoon with you some ideas on this newly developing field named the Kagome graphene. As some of you may realize already, the word Kagome must come from Japanese language, and it does. It's a new two-dimensional material. As all of you know, or most of you at least know, graphene is a two-dimensional material. It's just a sheet of carbon atoms that was discovered. It was physically realized in the late 90s or early 2000s, and thereafter there's no looking back. A lot of people working on graphene, which holds a lot of promise for new materials and applicable materials to industry, industrial products, and so on and so forth. I'll talk about a particular type of graphene, this new kind of graphene that is just sort of evolving. It's called the Kagome graphene, and what you see here is a little basket showing you a certain pattern of hexagons and triangles. And if I go on, you see another picture of a similar basket, and more clear perhaps, and lots of oldies like me would remember their wife handing them over this little bag of triangles and hexagons to go to the market and buy them something for the day's cooking at home and so on. Now, a Kagome lattice, as you have seen already, consists of an arrangement of shapes whereby 2 triangles and 2 hexagons surround every node of the lattice pattern in what is called a tri-hexagonal tiling. And you see the picture of this tiling in this slide. The term Kagome is derived from the Japanese word, as I said already, Japanese word kago, meaning basket, and me, meaning eyes. A basket with eyes, in other words, is what is meant by Kagome. The name Kagome comes from the old Japanese art of Kagome weaving. The Japanese were very good weavers in the old days, and they could weave these kind of designs with triangles and hexagons in the pattern, and in the Kagome weaving, bamboo baskets are woven in the same pattern and leading to these different objects, like the example of baskets that I showed you, baskets or bags. And coming now to the nitty-gritty details of the Kagome graphene. Graphene, I told you, is just carbon atoms arranged in a 2-dimensional sheet. And Kagome graphene is characterized by a regular lattice of hexagons and triangles, as you see in this picture. It behaves as a semiconductor and may also have unusual electrical properties, as I will discuss in a moment. So you see here, there are these atoms, carbon atoms, which are arranged in hexagonal patterns, and the triangles. Here's another picture of the structure, and the radius, the diameter of the circular part, as you see, is 5.38, 5.4 angstroms. This picture displays the structural parameters and electronic properties of 2-dimensional carbon allotrope graphene with a Kagome lattice structure. So it's just graphene with a different structure. And here you again see 2 pictures, A and B, of the atomic structure of Kagome graphene. And you see here the dashed red or brown part of the picture on the right-hand side of the figure A is giving you the the unit cell, the basic unit cell of the structure, whereas the red dotted figure in the same part A shows you a larger unit cell of the same structure. And the atomic structure of Kagome graphene, where the primitive unit cell is shown by the dashed red line, as I mentioned. Blue and green triangular rings of atoms are 2 sublattices of the system, as you see here, blue and green. These are therefore the triangular rings of the atoms, which form 2 sublattices of the system. And the dotted brown line towards the left of figure A shows a square root 3 by square root 3, in the jargon of solid state physics, supercell, as a result of Wigner crystallization. Now, Wigner crystallization, for those of you who don't know about it, is a crystal made not of atoms but of electrons at very low temperatures. Under certain important conditions, electrons can be made to freeze into a crystal structure, and this idea was predicted by the great Wigner long time back, but was not realized until a couple of decades back. So you can see Wigner crystallization taking place with the in the Kagome graphene structure. The part B of the figure shows the Kagome graphene, which is different than Kagome graphene, where the triangular rings are linked by acetylenic carbon linkers. And those of you who are chemistry oriented would easily see that there are these acetylene linkers, carbon linkers in that crystal, or in that lattice, or in that two-dimensional structure. All right, coming to the theoretical analysis of such materials, you can calculate the energy band structure, the so-called EK relationship, K being the momentum vector or the wave vector of the lattice wave vector of the electrons, and you get these figures. The red curves in the figure on the left, figure A, corresponds to the spin-up electrons, and the dashed blue curves correspond to the spin-down electrons. And this is the band structure of Kagome graphene for a square root 3 by square root 3 cell with 5 holes doping. That is a 1/6 filling factor for the flat band. Charge densities for states in the occupied flat band in A, forming a Wigner crystallization, and part C shows the magnetic moments of the atoms in a square root 3 by square root 3 cell. The magnetic moment of atoms in the closed circles is 0.055 Bohr magneton, while those this B should appear as a subscript rather than a multiplier, by the way. So there's a mistake there, or something happened in going from computer to computer. While those of other atoms are minus 0.021 Bohr magneton. So you can see the density of states here. I don't know if I can, yeah. The density of states, partial density of states is plotted here. So here the energy is along this vertical axis, whereas the figure on the left shows the band structure. And as you see, you have a more or less flat band corresponding to this Kagome structure. The band structure of Kagome graphene, where the solid and dashed lines are results of density functional theory, which is a very popular tool with solid state theorists, and the tight binding model respectively are shown in the part A, as you've just seen. Inset shows the wave function for a localized state in the flat band, and partial density of states, PDOS, of the Kagome lattice in the part B. Theoretical calculations predict that the compound known as Kagome graphene should have completely different properties to graphene, because it has flat bands. Kagome lattice with new properties. This is very recent work, appeared in 2021, this year, in Angewandte Chemie, which is International, which is German for Applied Chemistry International, edition 2021. And what is shown by this research is, which was carried out in the Department of Physics and Swiss Nano Science Institute at the University of Basel in Switzerland, in collaboration with the University of Bern, again capital of Switzerland, have now produced and studied Kagome graphene for the first time. As reported in the journal Angewandte Chemie, these investigations have delivered promising results pointing to unusual electrical or magnetic properties, as shown in the previous diagram, where I've shown you the magnetic moments also, along with the density of states, etc. To produce the Kagome graphene, the team applied a precursor to a silver substrate by vapor deposition. So you have a silver substitution, a silver substrate obtained by vapor deposition, which was then heated to form an organometallic intermediate on the metal surface. Further heating produced Kagome graphene, which is made up exclusively of carbon and nitrogen atoms and features the same regular pattern of hexagons and triangles. So this is the recipe that these researchers in Switzerland used to produce Kagome graphene sheets. Scanning tunneling microscopy and atomic force microscopy were used to analyze the structural and electronic properties of the Kagome lattice. The scanning probe tip used in these studies was terminated with a single molecule of carbon monoxide. It was observed that electrons of a defined energy, which is selected by applying an electric voltage, so if you vary the voltage between the tip and the surface, you can select electrons corresponding to different energies. This is the normal way spectroscopy is done using STM or AFM. So it was observed that electrons of a defined energy, which is selected by applying an electrical voltage, are trapped between the triangles that appear in the crystal lattice of Kagome graphene. This behavior clearly distinguishes the material from conventional graphene, where electrons are distributed across the various energy states in the lattice. In other words, they are delocalized. So this is the important thing to appreciate, that in the normal conventional graphene, it is amazing how the speed at which this science in these kind of structure studies is developing. We were really talking about conventional graphene as though this is something which was done 100 years back or something. It's so recent as early 2000s. The localization observed in Kagome graphene, so as opposed to the normal or conventional graphene, where the electrons are delocalized in the various energy states, here in Kagome graphene you have localized electrons, as I discussed a minute back, along the triangles. This localization is desirable because it causes strong interactions between the electrons, and in turn these interactions provide the basis of unusual phenomena such as conduction without resistance, so the so-called superconductivity. So you see, you have strong interactions between electrons, and that should already remind you of superconductivity, where you have the formation of Cooper pairs as a result of strong interactions between electrons which overcome the electrostatic repulsion, and thereby leads to superconductivity. So you see, this is a fantastic novel material which can show promise for as diverse phenomena as superconductivity. These studies, apart from semiconductivity, these studies also revealed that Kagome graphene features semiconducting properties. In other words, its conducting properties can be switched on or off as with a transistor. In this way, Kagome graphene differs significantly from ordinary graphene, whose conductivity cannot be switched on and off easily. Graphene, ordinary graphene, if you form a layer, it's either semiconducting or metallic. But here you have a possibility of controlling the conductivity, thereby leading to the formation of devices such as the transistor and so on and so forth, which will be much faster, of course, than the ordinary crystalline silicon or any other semiconductor material. In continued further investigations, the team plans to detach the Kagome lattice from its metallic substrate and study its electronic properties further. So you see, in the example that I mentioned on the research work done in Switzerland, you had a Kagome lattice film, single atom film, on top of a metallic layer of silver. But now the same workers intend to be able to detach the Kagome lattice film from the metallic substrate and study the electronic properties in greater detail. The flat band structure identified in the experiments, meanwhile, supports the theoretical calculations which predict that exciting electronic and magnetic phenomena could occur in Kagome lattices. These investigations already project that Kagome graphene could act as a key building block in sustainable and efficient electronic components, according to the authors of the reported study. Here is another example of a very useful application of the Kagome lattice. Kagome lattice in photonics. Photonics, as you know, is a rapidly developing field, and the chief attraction is that here, instead of the material particles called electrons, you want to do things by playing with photons, which of course travel at the ultimate limit to velocity of light. So these are promising fast communication kind of devices or materials. So as the photonics industry continues to develop new and better fiber laser and supercontinuum laser sources, special optical fibers such as photonic crystal fibers are a hot topic of particular current interest in Kagome optical fiber. And here is a real example of this application. Kagome air core microstructured polymer fibers, which are shown on the left in figure A, are a new class of broadband terahertz waveguides with low loss and low dispersion characteristics. And in this figure, the caption is given here. The micrograph, you have a micrograph of a Kagome PMMA fiber. PMMA, polymethyl methacrylate, is the same material which is commonly used for making your artificial lenses for the eyes, which ladies, of course, love to use to change the color of their eyes, etc., etc. So it's the same material. A micrograph of a Kagome PMMA fiber shows its lattice structure and hollow core in the figure A, which has just gone. The terahertz TDS setup used to characterize the fiber section, magenta color in the previous figure, includes an acousto-optic modulator, two off-axis parabolic metal mirrors, a photoconductive antenna, and a symmetric pass lens. So you have a complete working system here on a Kagome lattice structure or crystal. So you see, this should show you the great promise that this new material holds, both in terms of the basic fundamental solid state physics, the new kind of physics that this material seems to show, and the applications of this material to at least two domains, the electronic devices domain and the photonic devices domain. I haven't touched upon the application in the superconductive materials. There has very recently, in the last couple of months, been important progress in that area too. So you see, this Kagome lattice structure is not just a theoretical novelty, but it's going to be useful for various applications that the examples of which I've just given you. I thank you for that.
So many thanks, Professor Zafar Iqbal, for your research into new structure for Kagome graphene 2D material. Please take a seat here, because I think we'll take questions right at the end. So if you don't mind, take a seat here, please. And in the interest of time, if I request our all invited speakers to keep their talk for 15 minutes so that we can go for lunch on time. So you won't mind. And I know there will be a lot of questions, because you touch upon something to do with the eye color, so I can see that there were some eyebrows raised from women's side. So any private question during lunchtime, please, not in here. Okay, so it is my pleasure to invite our next speaker, who is Professor Noor Muhammad Butt, sir, who is going to talk about current status and future trend in pico technology. I'll just say one or few words for you, because if I spend all time, it will be 15 minutes. So he's a professor, Preston Professor of Nano Science and Technology and chairman of the Preston Institute of Neuroscientists. He is a very coveted researcher from PhD and DSc from Birmingham University, published many books and many seminars. He is recipient of many international prizes, to note few: Senior Humboldt Award Germany, Khwarizmi International from Iran. A list goes on. So if I spend all time, I think we'll be sitting for lunch here. So please, sir.
Bismillah ar-Rahman ar-Rahim. My dear friends on the chairs, Dr. Khurshid, very long time colleague, INSTEC, Dr. Zafar Iqbal, long time associate, and Professor Hafiz. Thank you very much. And audience, I'll be very quick. I'll introduce one new thing of concept regarding the education of nanotechnology, because nanotechnology has been evolved as an industrial revolution, and therefore there was a concept some years back, 10 years back, when we started this institution. There should be trained people to get their best contribution from in the field of nanotechnology. And therefore, I gave a concept of a multidisciplinary degree at BS level. BS is a very important level which is going to enter into higher studies, into the industries and job employment, and therefore this is a stage where multidisciplinary education is very important. And in that concept, I'll go quickly over the area in the 15 minutes I've been given. The concept is that we are teaching in this institute, which is a private university, Preston University, is the only one institute in the country giving this multidisciplinary degree, teaching physics, nano-based of course, chemistry, biology, and material science in 132 credit hours. The important point is we had a very fortunate faculty of 6 full professors, very well experienced, from Qaeda University, retired, and Atomic Energy Commission. This was the crux of the matter, the good faculty which designed a new scheme of studies at the courses, 43 courses you will see quickly, which we are taught. And the central point is that the benefit of this multidisciplinary degree is that world over this institute is fairly well known, and so far in the last 10 years we have passed 65 scholars with BS Nano degree, the only one in the country, and one of the 30 institutions in the world with the multidisciplinary concept at the time. And now there are 100 such institutions in the world which are giving multidisciplinary degree, where sometimes 2 subjects are combined, sometimes 3, and even sometimes with physics and chemistry, engineering subjects at BS level are combined. So this is the central piece of my seminar, and I'll quickly go to describe its benefits. At the end, since my talk is mentioned as a PICO technology, which a couple of years back I gave a lecture on this, so I'll touch upon those PICO technology in addition to the nanotechnology, which is creating other wonders apart from the nanotechnology. So quickly we'll go to the concept of multidisciplinary degree. Anyway, these are some of the things which have, my life has been spent mostly at the Atomic Energy Commission, Government College Lahore, where MSc in Physics, the central basic degree in 1957. And the institute, PINSTEC, some of you know, others should know this, the basic premier nuclear institute. And now currently, so basically, as you know, all are specialists in nanotechnologies. There is a simple definition which I can't, because there were a lot of definitions. It is the study, I think these words are important. Study the manipulation, control, and use of materials and their structures. So all this within the scale of 1 to 100 nanometers is the nanotechnology, as we know. So the importance is that there are 2 things are important. One is the scientific importance, where at this nanoscale, the classical physics fields and the quantum physics or quantum science comes in. So it's the other important is that it's the multidisciplinary subjects required for nanotechnology. And then very important contribution from economic point of view is the industry, all types of industry which are involved, and global marketing at the moment is some trillions of dollars. You can imagine 1,000 billions, $1 trillion of all the products. So this is world over recent figure. So it's a very important aspect. And basic concept is the surface to volume ratio is very high as the particle size becomes smaller. Simple mathematics. Yes. Economically, the Wall Street Journal has been sounding various signals on the importance as the industrial revolution. And you see the growth of this technology going up to trillions of dollars by this 2020s and so on. So it's a great contribution of this technology to the economic aspects as well. You see when in 2000 there were 60,000 workers, now in 2010 years' time, 10 times workers have increased, 60,000 workers in the field of nanotechnology. So it's a very highly important technology coming up. The concept that is a multidisciplinary in all types of technologies. You see all types of industries, from food science to cosmetics to computers, all types of industry, because where the thin nano materials are used, the applications become dominant. You see the websites, a lot of literature is available on the nanoscience and nanotechnology, and you can choose education, you can choose industry, you can choose whatever you like. These are the websites, this shows the importance. And then, of course, the carriers, all, sorry, in universities, in industries, in the various fields, you have the employment world over. Unfortunately, in Pakistan, I'll discuss, the industry is not coming up where they should have been. So next, I come to the central part of my talk in 10 minutes' time, is the human source development with the concept of a multidisciplinary degree. And the important point is why this degree is needed, because it's dealing with the industrial revolution, the nanotechnology, and there's a lot of influence on the society for the next few decades. Therefore, to meet the needs of industry and research institutions and various universities, you need qualified people in the multidisciplinary field. Therefore, properly qualified and trained human resource in nanotechnology for the best contribution is essential for all countries, whether developed or underdeveloped. So, if you see the word over the concept, I gave the title, this national and international importance I have to give. And the international importance, you see almost all countries have their BS. I'll touch upon the BS. In Australia, in Canada, in Denmark, and in Pakistan, we have only one institute with multiple degree situation at BS level. But we have at MS, some institutions in the country are giving the MS and so on, and PhD. But we are concerned with as I said, there are about 100 institutions now, such giving multiple degrees. So now we come to why the multidisciplinarity is important. You see all subjects are combined, but we are combining physics, chemistry, biology, and material science. But there are concepts that even engineering is to be integrated in some ways at the BS level. So it will be, a lot of nanofabrication is involved. Therefore, the concepts of engineering at this BS level are also important as being considered the world over. And of course, a new concept of medicine is coming, nanomedicine. It's a revolution. The treatment of cancer, the treatment of ophthalmological systems, new sort of lenses and things are coming up. So therefore, this will be, we are now interested in the nanomedicine, but it's as a part of small course. But I think word over much more is coming up. So you see in various institutions in the world, I've listed a few in Germany, in Denmark, where the multiple disciplinary concept is coming up. So we are just in the contemporary physics, in the teaching of nanotechnology. In USA, there are several universities in Drexel, in Louisiana, in Northwestern California, San Diego, and so on. So this concept I'm just putting up. Now, just in the next 10 minutes, I'll go to what we are doing in Pakistan. We have 4 years course, as you see, at BS level. In the first 2 years, we take pre-medical and pre-engineering both, and teach the basics of biology, basics of mathematics, which the pre-medical students do not study. So it's a very important aspect that in the 2 years, we give all the basics in terms of various subjects involved. And then the third and fourth year, we give the major subjects. And one important thing is that the research, one full semester is given to research, and the laboratories of the Atomic Energy Commission are open officially for our students if they want to do some research, and some institution in the country. So in a part of from our own institutions. So these are the subjects you see: mathematics, IT, and the all listed according to the requirement of the HEC, 43 subjects. But the important point I like to mention the social impact of nanotechnology, because new materials, new industrial materials are coming up based on nanotechnology. The public mind has to be set. Therefore, there is a concept that the nanotechnology, social science also should be discussed. It's the first time in the country that we are, with the technical degree, also given social science courses, 3 credit hours, and then introduction to psychology. So it's a very interesting course with the students, and the result is our students are being getting scholarships in 8 countries in the world, and 80% of our graduates have got already these scholarships, fully funded. It's very difficult. You know how to get the MS scholarships, but 80% of our graduates in 8 countries get these scholarships. The success stories, as Basel has been in the picture in the Professor Zafar Iqbal's lecture, they tried this multidisciplinary degree in early this century, and they have they are very short. Their graduate said that as a founder of some company, he is able to satisfy his customers because he has a multiple degree in physics, chemistry, and so on. So that's the advantage, and we have different type of advantages in our success story. And the important point is our placement of the alumni of in the MS and PhD after our graduation. In 8 countries, there are 35 students with scholarships. Pakistani universities also, NUST and so on for MS, and they have won 52 fully funded scholarships in 8 countries, which is, I think, a great thing, to an amount of 355 million. It's all recorded. It's a big amount, 35 crores of rupees. The students won as scholarship because of the multidisciplinary degree. So where the students are in China, in Hong Kong, in Norway, Germany, South Africa, Russia, Japan, Belgium, and in the United States. The important point is I would like to mention, the China has helped us very much. We have, when we started this institute, we had an MOU with China, and they were giving 3 fully funded MS PhD scholarships. And there are now about 30 students at only one institute, the best institute in Beijing on nanoscience and technology of the Chinese Academy of Sciences. And their students are doing PhD and MSc. And on their own, first contract was for 5 years MOU, and they extended because our interaction was very successful, another 3 years. This was the extension of our contract. These are different details of the students, I think I've just mentioned quickly. Now, the important point is that after the BS, the benefit of this multidisciplinary degree was that in other countries, the students won the awards. For example, in China, during the MS, this student has published about 19 papers during MS in high impact factor journals, factor of 30, 27, 10, and so on. So that's because of this good training they had in the multidisciplinary degree at BS level. And now there are many, at this particular institute in Beijing, there are 14 countries which are sending their students for MS. But this graduate is representing all these countries as a student of graduation as a PhD students from our institution. So Russia, this is an award from Russia. The student won during MS in addition to the scholarship. And in Pakistan at NUST, this girl got the gold medal in NUST in MS from the Dr. Mujahid's institute at NUST in materials in her MS. And very strange, this student did from Beria Management Sciences MS, MBA, and got the gold medal. So see the variety of the subjects and the students, good students get on to. As another university in Pakistan. Future of exotic is, as I mentioned, just finishing in the next 5 minutes, is the pico technology, an extension of the nanotechnology, 1,000 times more smaller and I don't know what sort of exotic applications will come up. Particularly, they are mentioning about the medical science, because now the treatment will be at the structure of the atom level. The nanotechnology, we were dealing at the atomic level and molecular level. One atom roughly has about 10 atoms is 1 nanometer and so on. But now we are going down to the 1,000 times smaller, and the application. Already a book has been written on applications of pico technology, which is this book, Pico Science and Book, and it's about 756 pages, mostly electronics and medical applications in terms of treating with this maybe neutrons and protons as an instrument for medical applications instead of the atoms and molecules as a whole in the pharmaceutical sciences. So the future, I think, before ending, there are different disciplines of science are converging as scientists have a common overlapping interests, and nanotechnology will promote the unification of most branches of science, engineering technology based on the unity of nature at the nanoscale, and social sciences and curricula for integrated degrees. This is what we are talking of future. And the other important aspect which I think should be dealt is the social sciences and ethics of it. Because new materials are involved, there are some toxic effects, there are some side effects of nanomaterials, and still internationally the regulations are being made. Already, in the science and the technology of chemistry and so on, regulations are there for toxic and safety of the workers. But on this pico technology and nanotechnology, regulations internationally not accepted as yet and not made. And this is an attempt which for future. One concept lost is the important point of contribution, that artificial brain is being coupled with the actual brain. And they are thinking by 2030 or 2040, a soldier will be available with two brains, artificial brain and the actual brain, and his efficiency will be more. And that is called cyborg warrior. And there's which will be an important pico technology applications. And the important part is, it's not going, what's happened? यार इधर आना जरा जा रही नहीं there's just two slides left. Yeah. Okay, so people are expecting that this cyborg soldier will be linking the human brain to the machines, and then efficiency increasing. A lot of new concepts coming up, and there's a fight. There's a race between China and the United States, whoever wins, to bring this cyborg warrior first. And these are some of the applications of pico technology, small satellites of the few grams instead of thousands of kilograms. So the recommendations, as I said, we should, in Pakistan I'll mention, one difficulty is that with this degree, the Publisher Commission has not recognized us yet. Therefore, jobs at the college level are not at BS degree. So we are now trying that so that the students, at the moment, only those who are interested in higher education, they come and get this education. But for general employment in Pakistan and industries, this is important that we should get this degree approved for teaching at an inter-level, because they are very well experienced. There are MSc in Lahore and in GIK and so on in nanotechnology. But at BS level, there is no institution in this country. So this is our faculty. You see all very well experienced faculty. Professor Fayyaz from Qaid-e-Azam, chemistry from Javed Iqbal retired, and some retired from the Atomic Energy Commission. And thank you very much.
Thanks very much, Professor Mohammad Butt, and sorry he has to leave to attend some immediate appointment, but many thanks for your talk. And I think about pico technology, and I think two things which I picked up was that the program education program which we are providing, it has not only sciences, but social sciences as well, industry and social science and psychology. So that is very welcoming, and linked to my theme, which I was saying earlier on, that I think we have to see the application, consumer, whatever invention you're doing. And the second thing was that about your students, and how they are getting acclaim outside the country and making, the Pakistani as an intelligent nation. So I think that is true worthy of that. So I think thank you for your work, because I'm taking the liberty asking question because you'll be leaving soon. So thank you very much, and it is my pleasure now to invite my co-chair, which is Professor Syed Javed Khurshid, and he's a man of few words. He doesn't give away anything, so I don't want to introduce him, and I'll let him to introduce himself. But it is honor, sir, that if you can come and share your thoughts for next 15 minutes.
Bismillahirrahmanirrahim. Professor Khalid asked me to introduce. I said just one word. After doing 45 years of my active life, I'm now working as a think tank at the Center of International Strategic Studies as a senior research fellow, and working on the weapons of mass destruction. WMD is my basic field in which I'm working, looking after the CBRNE, means chemical, biological, nuclear, radiological, and explosives things. Here, when Zafar invited me to come, I said I must speak on something which is very different and don't come in the purview of the educationalists, researchers, professors, and should give a little importance to that, because sometimes we think about the things after 10 years or 15 years when they have already gone to the stages when it is difficult to handle. So today I picked the topic of emerging technologies, and nanotechnology also comes inside the emerging technologies. It is one of the emerging technology. I will name those technologies afterwards. Right away, the world is considering 7 to 8 technologies as emerging technologies. And these technologies are rapidly changing the world. And after 1 or 2 years, things are going to be very, very different. Let me tell you. Because they are going on that space which we can't imagine sitting in Pakistan. Because daily so many papers, so many innovative technologies, so many innovative findings are coming that it's difficult to keep track of them. Well, I'm very happy that some of the portions, the industrial relations covered by Khalid Saab, and then Professor Bhatt has covered the education systems and how we are going to educate. But some of my slides will be repetitive, but they are important to grasp the technology and to handle the technology. So I will go rapidly on them, and then I will come to the point. Okay. The definition is already covered, but actually this is the technique, the handling and things are in this definition. And this definition and this description of the nanotechnology is going to give the importance. Nanomaterials, as Bhatt Sahab already mentioned, you have seen that, but this properties comes due to a small size and large surface. For example, in a material melting points, color, strength, chemical reactivity, and many more things changes at the nanoscale. Nanotechnology can be very beneficial, as you have seen, and have the potential to make a significant impact on the society. I am taking the word society and giving a lot of importance to that. Nanotechnology has already been embraced by the industrial sectors such as the information and communication sector, but it is also used in food technology, energy technology, as well as in some medical products, as mentioned by Bhatt Sahab. And medicines. Nanomaterials may also offer new opportunities for the reduction of environmental pollution too. Okay, so advances in nanotechnology have increasingly been facilitating novel applications in a wide range of fields, including materials, electronics, photonics, biotechnology, and life sciences. This ability to design and manipulate molecules with specific properties at the nanoscale level allows scientists to achieve outcomes that are of potential uses in the hostile uses also, but by no means limited to this beneficial uses. Increased electrical efficiency of solid-state laser weapons is one of the examples. Now, if we see health sciences, nanoparticles can have the same dimension as some of the biological molecules. See, we haven't considered that. And can interact with the human body. In human and in other living organisms, they may move inside the body, the blood, reach the organs such as liver or heart, and may also cross cell membranes. Insoluble nanoparticles are a greater health concern because they can persist in the body for a long periods of time. The parameters of nanoparticles that are relevant for health effects are nanoparticle size. Actually, it is a size which is very dangerous. Chemical composition and surface characteristic beside that, and shape also. Inhaled nanoparticles can deposit in the lungs and then potentially move to other organs such as brain, the liver, and the spleen, and possibly the fetus in the pregnant woman. Some materials could become toxic if they inhaled in the form of nanoparticles. Inhaled nanoparticles may cause lung inflammation and heart problems. The objective of nanoparticles used as a drug carrier is to deliver more of the drug to the targeted cells, as you talk about the cancer cells, to reduce the harmful effects of drug itself on other organs or both. However, it is sometimes difficult to distinguish the toxicity of the drug from that of nanoparticle. With the exception of airborne particles reaching the lungs, information on the behavior of nanoparticles in the body is still minimum. Assessment of the health implications of nanoparticles should take into account the fact that age and respiratory tract problems and the presence of other pollutants can modify some of the health effects. Information on the effects of nanoparticle on the environment is very scarce. However, it is likely that some conclusion drawn from the health studies can be extrapolated to other species, but more research is needed. Food safety. Nanoadditives have been shown to be effective preservatives. Nanomaterials have also been used to create new flavors. Non-encapsulation has been used to mask undesirable tastes. Nanoparticles have also been used to monitor toxicants in food and environmental samples with high sensitivity. Energy and environment, nanoparticles are used there to generate power, have been investigated, from exploitation of electrical quantum dots to improve solar cells and all other things. But I will go rapidly on that. Delivery systems also developed. Nanotechnology will enable new delivery system and methods to avoid counter-terrorism. Enhance blast and detonation parameters of blast weapons such as thermobaric explosives using nano-energetic composites. Recently, you might have read an article in the Newsweek too about the nano vehicles, self-organized manner with the use of swarm technologies. So you can use the swarm technology using nanotechnology, any one of in the swarm carrying the materials, which is dangerous. So you cannot detect it. And control sustained delivery of biochemical agents. Okay, nanotechnology is affecting all the aspects of life. I have chalked those down, and they have been discussed by some of the speakers before. And I will go rapidly on that.
Interruption. So, एक मिनट, डॉक्टर भट्ट साहब चाह रहे हैं उनको शील्ड देना. Okay, fine, done.
Okay, my topic actually starts from here, dealing the nanotechnology from this point. Threats. What are the threats of nanotechnology? The diffusion of nanotech may increase the likelihood of nano-enabled terrorism. As nanotech is increasing, cheap and user-friendly nanotechnology hardwares and open source instructions are readily available with them. This is very dangerous. Nanotechnology will make it easier to state actors to develop or use advanced chemical and biological weapons. The potential of new nano-enabled capabilities will accelerate arms race and undermine static stability. Problematic is to control dual use. So we have to be careful about the dual use of nanotechnology. And the researchers should know what are the dual uses of this thing, what they are doing. Offensive, it can be offensive, it can be defensive. As such, R&D cannot be stopped. See, in all these research, in scientific research, in scientific developments, everything, every small thing, everything has dual use. But you have to weigh that are you getting more benefits or it is more dangerous? Or if it is beneficial, how you can control the offensive things, the dangerous things for the benefit of the mankind. So you have to save the mankind. Whatever you are doing for the mankind, to benefit the mankind and to save the mankind. There are two things. So you have to be careful when you take research. I have given a guidance to the universities. I have given lectures to the departments of the universities. Because in Pakistan, see, what I'm saying is not in my topic, but what I'm telling you, I have told them that they have to form the research committees. And the research has to go through those committees before it is approved. And it is done all over the world in developed countries. Like Americans, they have 7,000 committees which controls the research and guide the research and approved it before publication and before approved as a project. So this proposal has already been given to the universities for last 2 years. It also had the export controls laws in it. Because see, we don't care, we are sending the microbes from our country outside and bringing them into at the name of research. That is very, very dangerous. Okay. Nanoparticles are far more reactive and unpredictable than normal chemical and biological particles. Nanotechnology has accelerated existing threats and created more novel and more complex threats. A more proactive policy framework is needed for that. Nanotechnology, chemistry, biology applications will go beyond weaponization of pathogens and toxic substances. There is a need of assessment of nanotechnological developments and relevance to chemical weapons control, CWC, biological weapon controls, BWC, Vacciner arrangements. These are the organizations which are helping to control these chemicals and biological materials. And I haven't discussed here and mentioned, there is an Australian group which also controls the chemicals throughout the world, how they should be regulated. And the resolution 1540, this is a UN resolution 1540, which controls the export of the research materials and other materials which can be dangerous, or before exporting them, you have to mention that where they are going to be used and what are their uses. long as the types and quantities are consistent with such purposes. See, you have to mention that for what purpose you are doing that research and for what purpose you are sending these chemicals outside of the country and bringing it in. And devices specially designed to cause death or other harm through the toxic properties, and any equipment specifically designed for use directly in convention with the employment of mutations and devices. The convention defines toxic chemicals as any chemical. BWC, the biological weapon conventions and toxic weapon conventions, controls indication that we have reached a critical point in nanotechnology, but not yet prepared to deal adequately with both the benefits offered and the potential risks posed by the advances in nanotechnology. In relation to biological and chemical weapon convention and resolution 1514 Wassenaar arrangement, there is an urgent need to review the development on relations to the BWC. First time it was considered in 7th Review Conference in 2010. Recently, after the COVID-19 and all these things coming up, there is a 9th convention coming up in the last week of December, and I have written some recommendations for that convention, and it has been accepted, and if the conventions take place, they will be considered there. State parties to BWC has recognized the implication and paradigm shift with respect to the prohibition on biological warfare and emergence of new framework for development. There is a need of more frequent review. Now, these days, these conventions take place after every 5 years. So recommendation is there because the research is going in a very fast way, so the convention should be held every year. Instead of individual state parties, another recommendation, state parties assessment, a formal collective assessment should be made by the collective BWC bodies, participated by state parties, policymakers, scientists, industry, and civil society together to exchange ideas and to understand different aspects of the problems. Proposals are under consideration to ensure greater security, are under formulation and will be present in the BWC state parties. Biosecurity and strengthening the BWC should be the part of assessment of their relation to the experts. Okay, these are the articles which directly can control. There are like 24 articles in BTWC which regulates the things, but these articles, Article 1, Article 2, Article 4, 5, 7, and 10, they can regulate the nanotechnology. I can give you an example of reading one of the articles. Nanotechnology is marked by international collaboration and increasing global distribution of research activity, a potential to penetrate all industrial sectors and its dual-use potential, which wants its exports controls in order to avoid technological development. International cooperation is needed. Okay, so nanotechnology research will go beyond chemical, biological weapon to include also, because nanotechnology is nowadays, as Bhatt has mentioned, is used in cyber technology, robotics, artificial intelligence, 3D laser printing, and these are all the technologies which are emerging and making the change in the world. So this is the solution which I recommend for the state parties or for the people involved in it, or the government. By state party, I mean that the solution is not to ban these products or stop nanotechnology research, rather to systematically study the safety and security of nanomaterials and to ensure a communication flow between all stakeholders. By stakeholders, I mean industry, research, policymakers, the universities, institutions, everything comes in. Numerous European bodies are reviewing current legislation to determine whether nanomaterials and nanotechnology require specific regulations. While companies working with nanotechnologies wait for the outcome of this process, what measures are they going to take, if any, to ensure the safety of the workers and of their product? how do they cope up with the knowledge gap? So there is a knowledge gap. We are just doing the research, but we are not looking to the things that how we should keep a control on that and they don't be used for the bad purpose. European Commission Scientific Committee on Emerging and New Identified Health Risks is working on the nanotechnologies information. So it is suggested international law is required to govern the safety and security of nanomaterials. The major hurdle is the disagreement on what exactly is to be regulated. With this, I leave the proposal with you, the thinking with you, and just to show you that things which look like that, the scientists, whatever they are doing, what research they are doing, that research can be very beneficial for the humanity, but at the same time, it can be very dangerous. So they have to keep everything intact, and beside finding the best uses, they can also work on their bad uses too. So simultaneously, they can give both information to the humanity. Thank you so much.
Thank you, Professor Dr. Javed Khushi Saab. And I think I'll pick up two things from your talk, very, very useful one. I think, again, invention and scientific research is good, but I think two things which you picked up are very useful for universities to think about. One is the ethical consideration of anything. And if I give my experience, even any undergraduate project or MSc project, MBA project, it has to go through ethical approval at the university. And only then it is allowed. So if you're working on these smart materials, then that is very important. And second thing which you covered, I did talk about industry, and some of other colleagues talk about industry, is about the policy making and how the international laws and regulation fit into it. So to ensure that whatever you're doing is being safe not only personally and health-wise, but being safe in terms of credential, in terms of doing business and taking international work. You don't want to be in the dodgy lines anywhere. So that is very good take from your talk. And sir, can we invite you to come in front and accept your shield of honor in terms of your presentation in this conference? So please come over. Dr. Zafar, would we be able to?
It is always an honor
And it is my pleasure to call upon our next speaker and the last speaker for this afternoon gathering, because Professor Richard Baker, he has presented his slides, so I think participants will receive his copies of his slides maybe afterwards, so we can do that to save time, and we don't want to delay you after lunch, for your lunch and your prayer. So let me invite Professor Dr. Muhammad Zakaria Bhatt Saab come and give his talk, which is on structural parameters of polystyrene materials evaluated by Sher-Williamson Hall side strain plot. And sir, I won't be able to say much about your credentials with the Government College University, so if you can introduce yourself to do with full respect.
My last position at Government College University was a Rafi Chair Professor in Experimental Physics. And I am Fellow of the Pakistan Academy of Sciences and President of the Pakistan Institute of Physics. I think that is enough. Oh. I will speak about a problem which postgraduate students usually meet in their research work. This is based on my experience as supervisor of research projects and examiners of MPhil PhD thesis. The structural parameters of main interest for those students who are working in materials they encounter, they determine the structure of the material and correlated it with the properties, mechanical properties, electrical properties, etc. And they come across the term crystallite size. And often there is confusion between crystallite size and grain size. So I will elaborate these things with the help of analyzing the XRD patterns of unirradiated and laser irradiated polycrystalline zinc. So a comparison will be made. The values of crystallite size will be determined by using different models, and then we will make a comparison which model predicts what. And the most favorite model which the students use is the Scherrer method. And I will point out the shortcomings of this model, and this model should be used but with certain precautions. In this figure you can see that materials have different structures. One is, A is the monocrystalline structure. In this you will see that all the atoms are arranged in the same pattern throughout the crystal. But in crystal B, you can see different regions in which the atoms are arranged in a regular fashion, but in a given area, but they vary from area to area. So this is called the polycrystalline material. And in amorphous material, there is no regularity in their alignment. This is an actual photograph optical microscopes of 5,9 pure copper, which is white grain, 0.9 mm, a big grain. Now, if you look at the polished surface, you will find these grains, bigger grains, and each grain has different color. These shades are because the planes in each grains are oriented in a different direction. Their orientations are different. And you see that there are boundaries of each grain which separate it from the other one. Now the nature of these boundaries is amorphous nature, and within the grain, the planes are oriented in a given direction. This is the optical or TEM figure. But if you use X-ray technique, diffraction technique, then you will see that within the grain, there is, I have taken just this, a short square which reveals that if you see this grain through X-ray beam, then you will see that there are different small regions within this region which have slightly different orientations. Say, if this grain has 1-1-1 orientation, but within this grain, there are tiny regions which are slightly misoriented. And these are the crystallites which lie within the grain. These crystallites, they cannot be seen by TEM or by TEM or by optical microscope. Now, so you have grains which are separated by more or less sharp contours, normally observed by TEM or optical microgram. But crystallites are undistorted, coherently diffracting regions within a grain, and these are considered as nanometer-sized single crystals and are detectable by X-rays only. And in particles, you can have many grains. Now, these are these figures, they pertain to the unradiated and laser-treated polycrystalline zinc, and the laser shots used were 50, 60, and 70, 80, 90, and 100. That is with a difference of 10 shots. And you see that the diffraction pattern, anti-YAG laser, which is available in CASP. Anti-YAG laser, 532 nanometer wavelength, 6 nanosecond pulse width, 50 millijoule energy. Now, these peaks were identified with the help of this standard pattern of zinc. Now, these peaks have different heights and they have also different widths. Now, in Sharon method, usually the most prominent peak, for example, this 002 plane, is taken as the peak which is analyzed, and the grain size determined from this single peak is taken as the crystallite size of the entire sample, which is not correct. I will explain it further why it is not correct. Now, to determine why these peaks they get broadened, according to Scherer, the crystallite size effects makes the peaks broaden, and secondly, there are structural defects like point defects, dislocation lines, etc. in the crystal. They also contribute to the broadening. So, the breadth of the peak beta, it should be sum of the two, beta D and beta epsilon. Beta D is the crystallite size contribution, and the next beta epsilon is which is given by Wilson formula 4 pi tan theta. This is called the Williamson-Hall equation, which takes into account both contribution of crystallite size and lattice strain. This is contrary to Scherer, which only takes into account crystallite size effect. Now, how to determine the width? Broadening of the peak, you can select the data of that peak and you just fit it with the Gauss function, and you will get this curve passing through the data, and it will give you the full width at half maximum of the width. If you take it from the origin 9, it will directly give, and if you take it from origin 6, it will give you the width, and from width you can calculate. And from the width you can calculate the full width at half maximum. Full width of half maximum is the width at 1/2 of the intensity of the maximum intensity of the peak. Now, this Williamson-Hall has 3 models based on different assumptions. In the one model, known as uniform deformation model, it is assumed that microstain epsilon is uniform in all crystallographic directions. And based on this assumption of uniform microstain in all directions, this equation is used and the data is plotted b cos theta on y-axis and 4 sine theta on x-axis. Then you get, and by linear fit, least square fitting method, you get the line, and the slope of this line gives the strain, and from the intercept of this line you can find so the values of crystallite size D and lattice strain determined from UDM model, they are listed in this table too. Now this method has also another model, which is uniform deformation stress model. In this model, the basic assumption is that the stress is taken, not strain, but stress is taken as uniform, and an isotropic nature of the Young's modulus of the crystal is taken into account. Now from Hooke's law, stress proportional to strain, and this constant is Young's modulus. You replace in the original equation 1 the value of strain by sigma over Young's modulus. Then you will get equation number 3. Equation number 3. And now you plot the data between beta cos theta and this parameter 4 sine theta over Young's modulus, and again you will get the values of crystallite size D, lattice strain sigma, and lattice stress sigma, and lattice strain epsilon. In its third version, with uniform deformation energy density model, UDM can be used to, this model can be used to determine the energy density of a crystal, that is energy per unit volume. This model is given by this equation 5, and when you calculate the value of D and other parameters, this table gives the values of crystallite size, energy density, lattice stress, and lattice strain. So these 3 parameters, under 3 different assumptions, 3 values of crystallite size are determined. Now in this figure A, crystallite size has been plotted as a function of laser shots. You see that in UDM model, blue line, it goes to, on a radiation, its crystallite size increases to for 50 laser shots, and then it declines till it comes down to say 80, and again it attains a peak at 90, and at 100 it again falls. The variation of crystallite size with laser shots is identical in all the 3 models, but the magnitude of crystallite size that varies for a given number of laser shots. So is the case with lattice strain, and you see that the variation again of this parameter in the 3 models is identical, and when we plot lattice strain as a function of crystallite size, they are represented by a straight line. Why? Because crystallite size D and lattice strain epsilon, they vary in an identical manner. So one will expect that there should be a linear relationship. Now this gives the lattice stress and energy density as a function of laser shorts. Again, you will see that lattice stress varies in an identical matter, though magnitudes, they are different. So this is the Williamson-Hall method to determine crystallite size and lattice strain, and you will see that the value of crystallite size determined by UDM is small as compared to the predicted by other two models. Similarly, the lattice strain is minimum for UDM and it is less than the other two models. Now the second method which is used is size strain plot. In this case, the model equation is given by this parameter, and a plot has been drawn between d square beta cos theta on x-axis and on y-axis. So this is the equation of a straight line, and when you plot the data of the same XRD pattern, you will get this situation, and these are again straight lines fitted by least square fitting method. The values of crystallite size d, lattice strain, epsilon, they are listed. Here you see that sometimes this strain is negative and sometimes it is positive. When it is positive and negative, it means the strain is either tensile or compressive. Next method is Helder-Wagner model. Again, all these models, the basis that the wide broadening is due to contribution from crystallite size and lattice strain. Now the values determined by this model are also listed here, and the next is Wagner-Aqua model. I will now compare these values of these three models. Again, you will see that the pattern of variation with laser shorts is the same whatever the model we use. But for a given number of laser shorts, the magnitude is different. So is the case with lattice strain. And since the variation of lattice strain and crystallite size is identical, again we will expect a state direct relationship between these two parameters. So this chart gives us the comparison of Williamson-Hall, UDM model, UDSM, UDEDM, size strain, and Wagner-Aqua model, and you will see that in each model the value of crystallite size is different, and so same is the case with the lattice strain. Now the Scherrer method, which considers only the contribution due to crystallite size, that gives us this equation. If we plot the data inverse full width of maximum versus cosine theta, then we get these plots, and from their slope we can get the value of crystallite size. Here you see that the anomaly is that crystallite size values, they are coming negative and positive. Negative crystallite size means nothing. It is ridiculous. So if we plot a graph between crystallite size determined by Scherrer as a function of laser shorts, you will see that below zero, these crystallite values are negative and these are positive. So negative, positive values are meaningless. But interesting thing is that the pattern of variation dependence on laser shorts is uniform, identical to that of the other five models. So we cannot use, why these are negative? These are negative because we have ignored the contribution of lattice strain, which is due to structural defects like point defects, line defects, two-dimensional defects, etc. And in those models, when that contribution was considered, all the crystallite size values were positive, but the negative sign appeared only in the lattice strain. So the neglect relatively, or secondly, why these values are large. These large values are given by the fact that we are giving all the credit to the crystallite size and not the lattice strain. So the conclusion is that crystallite size and grain size are two different entities. A grain size may have two or more crystallites in it. Williamson-Hall size strain plot, Helder-Wagner and Wagner-Aqua models are appropriate methods to determine crystallite size and lattice strain of polycrystalline material. Scherrer model is not a realistic model to determine crystallite size for various reasons discussed before. However, in the case of nanocrystalline materials, that is when the grain size is less than 100 nanometer, a good correlation between TEM optical and XRD measurements regarding grain size, crystallite size is observed, because that grain is itself going to nano scale, so crystallite size and grain size, they become identical. So the most favorite technique which students use, Scherrer method, should be used very carefully, and other methods should be rather preferred instead of this Scherrer model. Scherrer model, another contradiction is that when we radiated zirconium with carbon ions, there all the crystallite size were positive. But in case of zinc, negative and positive values are observed. So one should be careful. So this is actually meant for the students, not for the senior persons. They should be careful while doing their analysis of the data. Thank you very much.
Thank you, sir. Thank you. Okay.
One technical question, just an layman question. Is the crystalline size and the strain has some relation? I mean, is the strain affect the crystalline size?
No, these are two independent things.
If these are two independent things, then why you are saying that
That's
the
why
Scherrer
we
formula
are-
is only for the size of the crystal. So if through Scherrer formula you are determining the size, then what
If
are
the linear relationship which I have shown between epsilon and d, if you like, I can show you that curve. You can see this figure C. Crystallite size versus lattice strain. There is, as crystallite size increases, lattice strain also increases. Crystallite size increase means that the crystallinity in the specimen has gone high and amorphous phase has gone down, which are the grain boundaries. So when crystal is there, bigger crystallite size is there, the atomic arrangement is tightly bound. That is tightly bound, so the lattice strain is more as compared to if there are more amorphous boundaries, so lattice strain will be less because amorphous phase is loosely bound atoms.
Thank you, sir, and thanks for your question. And I think it was very interesting talk. And as Professor Zakaria Bhatt Sahab, you said, a lot of work which we're doing in here is about, for the students to understand the basic ideas and fundamentals. And if you get the foundations right and any questions burning, I think that is something which needs to be clarified here. So I think that is something we must stress upon in this conference. Sir, I think as per tradition, this is the time that your contribution should be acknowledged and recognized with an award. So, Professor Zafar Ilyas Sahab, please do the honor. नहीं अभी नहीं चलानी है, बाद में चलेगी नहीं अभी 2 बज गए And sir, I think in the interest of audience, and I can hear some rumbling tummies there, I think lunch is ready. So if you don't mind, I think make lunch as an informal lunch. You can ask questions to our senior speakers, and let me thank everybody who came in here and all this contribution from our senior members.